Hello, this will be a demonstration of Proposition 6 from Book 2 of Euclid's Elements, which states that if a straight line be bisected, that is cut in half, and a straight line be added to it in a straight line, the rectangle contained by the whole plus the added straight line and the added straight line plus the square on the half will equal the square on the half plus the added straight line. You'll be grateful at how clear all the enunciations before now have been. That's nightmarish. But again, as with all other propositions, it becomes more clear once we draw it out, so let's do that. So let's describe our given. Well, what we're given is a straight line. I'm not going to show up as a... What we're given is a straight line. We'll call this straight line A, B, and it is bisected at point C, so we know that AC is equal to CB, and added to AB in a straight line, we have BD extended out like that. So the terms throughout this proposition, AB shall be referred to as the whole, AC and CB are both the halves, and the straight line BD is the added straight line. So putting all those, putting our given, or putting the enunciation in terms of the given, what we are trying to prove is that the rectangle contained by AD and DB what we're trying to prove is that the rectangle contained by AD and DB, so AD being the whole plus the added straight line, that's AD, plus the added straight line, which is BD, so the rectangle contained by AD and DB, plus the half, plus the square on the half, and so the half we're going to be working with is BC. So the rectangle contained by AD and DB plus the square on CB is equal to the square on CD, CD being the half plus the added straight line. So that is what we're trying to prove. Now, again, let's start by constructing everything. On the straight line, CD, we're going to make a square, CEFD, like so. We can do this by proposition 146. And we're going to join the straight line DB. Next, through point B, we're going to draw the straight line BG, like so. And then such that point H is the point at which BG and DB intersect. So through point B, we are going to draw the straight line BG such that it is parallel to either EC or DF. Next, through this point H, we're going to draw the straight line KM. So we're going to have M on this side, L will be here, and K will be all the way out here. And you know how far K is going to be out by the third parallel straight line we draw. Oh, KM is parallel to either AB or EF. And now, finally, through point A, we're going to draw AK such that it is parallel to either CE or DF. We have drawn all three of these parallel straight lines by proposition 131. So that's our construction. For now, or not for now, we should also note this gnomon right here, NOP, like that. So the gnomon NOP is going to contain this rectangle, and that rectangle. Okay, we're done with our construction. Now we know that the rectangle AL is equal to the rectangle CH. How do we know this? Well, we know that AC is equal to CB. And these two rectangles, AL and CH, are in the same parallels. So AB is parallel to KH. And so because these rectangles are on equal basis and they're in the same parallels, we can leverage proposition 136 and say that the rectangle AL is equal to the rectangle CH. Furthermore, we know that the rectangle CH is equal to the rectangle HF, because these are complements. This is proposition 143. And so we can say that the rectangle AL is equal to the rectangle HF by common notion 1. And by adding this little area, what area are we adding? Oh, I see. We're adding the whole rectangle CM, not the whole rectangle, just the rectangle CM. So to both sides, to both AL and HF, we are adding the rectangle CM. And so we can say by common notion 2 that the whole rectangle AM, which is composed of AL and CM, will equal the gnomon NOP, because this gnomon contains this whole rectangle right here and this guy right here. So we have equals being added to equals, the sums will be equal, common notion 2. So that is how we can say that the rectangle AM is equal to the gnomon NOP. Now furthermore, we know that the straight line DM is equal to the straight line DB. We know this by the porism of proposition 2.4, because this is the parallelogram about the diameter of a square. And so we can safely say that it is also a square. And it being a square, the side lengths are all equal. And so the two sides of the square BM, namely BD and DM, will also be equal. Again, that is the porism of proposition 2.4. We can then say that because the rectangle AM, so the rectangle AM is this whole rectangle right here, it's contained by AD and DM, and we've just shown, or not shown, but we know that DM is equal to DB, and so we can say that the rectangle AM, is equal to the rectangle contained by AD and DB. Again, I'll run through that. The rectangle AM is contained by AD and DM, because we have the rectangle. Now we know by the porism of proposition 2.4 that DM is equal to DB, and so we can substitute one containing side out for its equal. This is again a property of magnitudes. We've seen this specific one quite a lot in book 2, and so substituting one containing side out for an equal length, we can say that the rectangle AM is equal to the rectangle contained by AD and DB, because DB is equal to DF. We can also say, by common notion 1, the rectangle contained by AD and DB is also equal to the gnomon NOP, because both are equal to the rectangle AM, as we showed up here. There's common notion 1. And we can then say, again, by common notion 2, if we add this square right here, LG, we can say that the rectangle the rectangle contained by AD and DB plus the square on CB, we know that LH is equal to CB, and the square LG is on LH, and so we can say that the square LH is equal to the square on CB. So we can say that the rectangle contained by AD and DB plus the square on CB is equal to the gnomon NOP, these three areas right here, plus this square on LG. Because again, just common notion 2, equals being added to equals. And finally, we can see, it is self-evident, that the gnomon NOP plus the square LG will simply equal the whole square CEFD. So we have these three areas right here, plus the fourth area will equal the whole. So this is simply self-evident. And so we can then say that, substituting everything out for their equals, we know that the gnomon NOP plus the square LG equal the rectangle contained by AD and DB plus the square on CB. Furthermore, we made the square CEFD such that it is the square on CD. And so we can substitute that out for simply the square on CD. And so finally, we can say that the rectangle contained by AD and DB plus the square on CB is equal to the square on CD. And this being what was set out to have been proven, we are done with the proposition, therefore, etc. QED. I don't really have anything to say about this one. It's a little complicated, just trying to figure everything out. It gets kind of messy if you're not careful, but There's nothing new about this proposition. It's just all that we've seen before. So I'm simply going to end the video right here and move on to proposition 2.7.